Alright, we're looking at the static session here. I decided instead of holding a session somewhere that we would essentially do an online session because I don't know if everyone would be able to attend. So let's work a few problems. So let's look at problem 7.7. And in there, he wants to know the internal moment and the shear force acting at point C here. So one way to do this is to clip the thing completely. First, let's try to find our load. So if we look at our load, we'll see we have a load that is 1/3, or L over 3, which L is 6, and then 3, so that's 2. So it is a distance 2 from C that this load acts in. The value of that load is, value of that load is 4,000 pounds, which that's what's kilopounds, per running foot, 6 foot, but half of that gives us 6 times 2, or 12,000 pounds total. Again, if you look at this, that is the area in green right there. 6, 4,000, and then half of it. So what we're looking at is 12,000 pounds sitting right there. So it is as if you replaced with that. And 12,000 means you have to have a support over here and a support load here. Technically this one, since it's pinned the way it is, can take an X load. This one, since it's a rocker, it cannot. So what we'll do is sum the moments about B, make it plus in that way, and what we'll do is we'll have this load, which is, we'll call it AY, times that total distance of 12 minus 12,000 times 6 plus 2, or 8, gives me a reaction load of about 8,000. So what I'll do is just put 8,000. Since there's 12,000 down, 8,000 up, what do I have to add to the 8 to get 12? And that would be 4,000. Now, you've got a couple of choices. Since you're looking for the internal moment and shear at C, it might become easier to split the beam and look at the right end. So let's do that here. So what we did is we split the beam, we rewrote it here. Essentially what I've got is this 4,000. Now if I look at that 4,000, obviously I'm going to have a moment to offset it, and I'm going to have a shear. Now if I didn't have a moment, let's see what would happen. So I would sum the forces in the Y. Tells me that this one has to be 4,000 to offset that one. So in fact, the shear is equal to 4,000. Now, if I just had an object that was like this, where I pushed it here and pushed it here, would that be in static equilibrium? If I even pushed it with 1 pound and 1 pound? No, because the thing would start spinning. So I have to have a moment here as well. If I offset that moment so that it's dead still, that moment has to be equal to 4,000 pounds times the 6 foot across, or 24,000 foot-pounds. Now let's say I just enjoyed working hard and I had no common sense. So let's say we take the other end of the beam. What we'll do is say, okay, we're going to look at as if I clipped it on the other end. First of all, this load, if you look back up here, was 8,000. And the load here was 12,000. And it was 2 foot over. So first of all, you look at this and you say, I have to have a shear equaling to that value offset with that one. In other words, sum of the forces in the y equals 0 equals 2, and let's just say that's plus. And what we'll say is 8,000 plus v minus 12,000 equals to, or v equals to 4,000. Take the 12 over, subtract the 8 from it. Not too surprising. It was the same value you got up here. Let's see if the moment's the same. So here we'll look at that. Okay, let's see if the moment's the same. So let's say moment this way. Actually, what we're going to find out, let's go with it the other way. Doesn't really matter at this stage of the game. Moment equals to what? So what you do is you come in, you sum the moments, you make it say plus your sum of the moments about the point C, which was right here, and that equals 0. It equals to m. Okay, so plus 12,000 times 2. Why is it plus? Because this is if it's going that way, which is the same direction here. Oops. And then minus, because the 8,000 going around it that way. 8,000 times 6, or the moment, is equal to 8,000 times 6 minus 12,000 times 2, 24,000, and it's 48,000, or the moment. This drops that down to 24,000 foot-pounds. Again, the same value here that existed here. So that concludes this problem.